so good morning to all of you. It's a pleasure to start this webinar. So we are today addressing a very hot topic, that is the offshore energy that is expecting to grow in the coming years in order to help attaining renewable energy targets. It is known that offshore energy still presents a high levelized cost of electricity, and part of this high costs of the levelized cost of electricity, they come from the fact that it's necessary to make the interconnection with the onshore network. And so it's very important to find out the right solution to make this connection, and this can be done either via AC grid or a DC grid. And also regarding other, so in terms of offshore energy, we can have it in terms of wind energy or also wave energy. And so we have today two presentations, one by Bernardo Silva, that is going to address the topic of the provision of frequency support services by offshore farms connected through DC grids, and another presentation by Irina Temis that will address more the topic of wave energy. And so the presentation will be entitled Grid Integration of Wave Energy Converters, Research and Experiments at Uppsala University. And so at the Uppsala University, they have already a large experience in dealing with this subject. Uppsala University started in 2002 within the so-called Lysekil wave power project. And since then, the Uppsala University wave energy converters are a point absorber type with a direct drive linear permanent magnet generator, power takeoff, and a full conversion process of electrical power is required prior to integration into the grid. So there are quite interesting challenges also from the fact of trying to deal with the integration of wave energy, and this is very much results from the fact that the type of converters requires a specific and adequate approach in order to make the right connection with the AC network. So I will start by introducing Dr. Bernardo Silva. So he completed the master degree in electrical and computer engineering at the Faculty of Engineering of University of Porto. And then he did his PhD in sustainable energy systems also at the University of Porto. And in 2014, and since then he joined INESC and is very much involved in scientific and consulting projects in the area of integration of renewable sources in electrical systems, as well in steady state and dynamic analysis of electrical systems. And so he is also very much involved with the SIGRE activities. So Bernardo, it's a pleasure for me to introduce you, and please, the screen is yours.
Thank you very much for the introduction. Thank you very much for the attendees being here. Can you see my screen, please? Someone just confirm.
Yes, yes.
Okay, so
perfect.
Good morning. Today I bring a topic that has been part of the investigation in my PhD thesis and also in the European project FP720s. It's related with the provision of frequency support services by offshore farms connected to the DC grids. Here I said back in 2009, 2010, when I started this research, offshore farms, for me it was just wind. Now I see that we can have more than wind at offshore, and we are even working in different projects nowadays. But the motivation to this work was very much related with the need of integrating more renewable in the power system, reducing greenhouse gases emissions. And the European Commission has a very ambitious plan to have a lot of power coming from renewables, and especially to do so, much of this power should come from offshore farms. So in 2008, it was said that about 40 times and 100 times by 2030 in comparison to 2008 energy values coming from offshore. And to do so, back on the beginning of our research, we investigated the deployment of DC grids. And why? First of all, we use DC because we are talking about cable circuits, a lot of power, and big distances to the coast, which makes almost impossible transmitting power in AC. So why having grids? Because the grids, we believed, that can harmonize the costs, the connection costs, because we are creating a common infrastructure that can be shared by several players, and also can facilitate the development of European markets and increase the interconnectors, which is also a big topic and a hot topic that the European Commission is pursuing nowadays. So what is the grid, the DC grid? We have here a simple drawing of a DC grid, where we have two mainland grid connected to the DC grid, and the DC grid can help on transmitting the power from offshore wind farms to mainland. We have here different areas. When we were doing this research, I used to call this UK, and this is France, but can be other countries, of course. And the DC grid allows to have power flows from the wind farms to one of our other areas, and also power flows coming from one area to another. We are talking about here about HVDC converters, voltage source type. They are bidirectional, so basically almost all the power flows that we can imagine can happen on this shared infrastructure. So at the other side, we have the mainland systems, and at offshore level, we have the voltage source converters that convert AC power generated at offshore to DC, okay? So this is basically the infrastructure of the DC grid. So if we attain a big deployment of these DC grids and a lot of offshore power coming from these DC grids, we need also to maintain the controllability of the power systems, the mainland power systems. So what is happening in onshore, and it happens for quite some time, is that onshore wind energy converters, they are able to provide what is called primary frequency control. Now it's frequency containment reserve, because they sense the frequency at their terminals, and they can change the pitch angle of the wind turbine blades. And if they are operating below the maximum capability curve, they can even provide upwards frequency, upwards power control. So when we have an under frequency, we can inject active power by increasing the amount of energy that we are collecting from the wind. It would be very good if offshore farms could do so, because we will not lose as much as controllability in the power systems, especially in scenarios where we have a huge deployment and a huge integration of these farms. Nevertheless, let me put my animation. The DC grid is a black hole for frequency events and for voltage events. So the DC grid decouples all the interconnected areas in terms of frequency and voltage. So the offshore wind farms do not sense frequency deviations, even though the turbines are able to provide frequency support. By using this technology, we are disabling this functionality. What should we do? Should we rely on communications? This was our first step. And to rely on communications, we could have a point-to-point communication, would be very complex. Or on the other hand, we could have a centralized control that would, I would say, talk to every player, measure, collect the data, and then process and send set points to the players. But here we have, first of all, we will be relying on the reliability of communications, which sometimes may not be very good when we are operating a system complex like this. And also we may have delays on communication, have to receive, compute, and send. So there is a quite big time frame to deal with. So we proposed another approach in this work, which consisted on using local controllers and exploiting a cascading control scheme. What is that? The idea was to reproduce the disturbances, the frequency disturbances, as small DC voltage disturbances. This DC voltage disturbance would be almost instantaneously sensed in all DC grid terminals, and then offshore converters, sensing that a voltage deviation would occur, would be able to play a frequency disturbance at offshore grid, because they are, it's important to stress, they are grid forming inverters for the offshore farms. So they set the voltage and the frequency at offshore AC internal grid. So they are responsible for setting the frequency, so they can slightly change the frequency at offshore level. So it was expected that this way offshore farms with frequency control capabilities would be able to provide a contribution, namely injecting more or less, depending on the frequency disturbance, active power to the HVDC grid, and hopefully this power would be channeled towards the zone that is more in need, the zone where the disturbance occurred. To do so, we implemented over the normal droop control, the active power DC voltage control, we implemented a supplementary controller that is intended to operate just in case of emergency. Let's call emergency when we have frequencies out of this interval. I mean, when we need, in fact, a contribution coming from the farms. And this new control rule, what it does, it's basically, it reduces the voltage according to the frequency deviation that is sensed on the AC mainland terminal. Of course, the opposite may also occur depending on the frequency deviation direction, okay? So on the other hand, we had also to endow offshore converters with the proper control characteristics to set the frequency change at offshore grid. So we are measuring the DC voltage, and when we have a disturbance, we proportionally to this disturbance set a new frequency at offshore level. So this is the basic control of the grid for frequency disturbances. And if we look to the grid, when we have a load disturbance here on mainland, for this case, it was a load increase of 150 megawatts. We can see that in the first case, let's look to the blue dashed line, without power frequency control capabilities, no DC voltage disturbance was verified. So the converters were doing as supposed by blocking frequency to the DC voltage. We can see that we have a quite big frequency excursion in area 1. In fact, it was there that the problem existed, but this frequency deviation is not shared among any other player connected to the DC grid, okay? Nevertheless, when we put our control on, the control I have just presented, we have the green line results. So we can see that we start having voltage disturbances. We can see that we have less frequency excursion in the affected area, and also that we have frequency excursion in the other areas. Why this is happening? Because the control is operating well. In fact, this control, and again looking for the green lines, enables the power injection towards the affected zone, as we can see here. And this power injection is achieved by two means. The unaffected converter, the onshore one, area 2, will also help on mitigating the frequency excursions. And this is why, going back one slide, we can see that there is a small frequency disturbance on area 2. So we are sharing the problem between the two areas. And also the power arc is coming from offshore farms. We can see that they are able to pitch themselves and start generating more power because they had that reserve margins. It's important to stress. So this power is also channeled towards the affected area. So the concept with these simulations proved to be feasible. And also we wanted to try another thing, which was inertia emulation. So we wanted to check if it was fast enough to capture the inertia emulation. The inertia emulation was set back on the time using the derivative of frequency. So we are able to quickly extract kinetic energy from the wind generator by relying on the derivative of frequency and inject this in form as active power to the grid. So the idea here was to check first if we could do that, and second, if we could inject, and in third place, if it was effective channel towards the affected area. So as we can see with these results, by adding to the primary frequency control, by adding this frequency inertia emulation capability, we can see that the turbine is able to quickly increase the amount of power that is then reduced due to the loss of kinetic energy. This is a normal behavior. But more important, we can see that this was channeled towards the affected area. So it proves to be effective even for these disturbances. And the impact in frequency can be measured in the rate of change of frequency, which is reduced from one case to the other. So with this, I finish my presentation related with the primary frequency control. I would like just to stress before saying goodbye that we tested this control technique for more layouts in simulation, and then we were not satisfied. We had a project led by Professor Carlos Moreira and funded by the Portuguese Foundation of Science and Technology called QMUT DC. And in this project, we tested at reduced scale in laboratory this control scheme in VSC converters using power hardware in the loop. We have an OPAL setup at INESC TEC. And also we proved that in real application, this control could be done. And we achieved good results. But the time is short. I just brought these results today for the sake of this presentation. So from my side, that's what I wanted to present it today. Thank you very much for your attendance.
Thank you very much, Bernardo. Thank you for keeping the time so well. I have two short questions for you.
Please.
First one, can you explain which best tool to analyze power quality problems?
Sorry, I didn't hear you.
So can you explain which is the best tool to analyze power quality problems in this case?
Oh, okay. Okay. It's different from the presentation I brought today.
Yeah.
Power quality, I would use Silent to analyze power quality, perhaps because it's the most complete suite nowadays, as far as I know, to do so. And we would need to have a good characterization of the converters, namely in terms of harmonics, but it's a different analysis from the one performed here. But yeah. I would say the Silent power factor would be the
okay. Thank you. Again, it seems that harmonic distortion is a very interesting topic. There's another question regarding harmonic distortion. So what type of harmonic emissions challenging you have faced? I know your presentation was not about that, but I don't know if you can provide some answer.
Yeah, I can. As you said, this presentation was not about it. We are relying on models, simulation models that do not look for the harmonics. The harmonic content is an issue, but I know that manufacturers are struggling to comply with regulations. We have several, and they are trying to comply with that. But this was not the scope of this study. So this part was not even modeled. We are working here in a different time domain, and we are not analyzing these small, I would say, small time variations and harmonics, because this here was done by using RMS simulations. If we do a complete simulation with harmonic, we would still be simulating some of the things, because the computational time increases quite much.
Okay, thank you very much, Bernardo. Can you stop sharing your screen? We should move on.
Let me just stop.
Yeah,
here.
so we are now passing to the second speaker in our webinar. Dr. Irina Temis. She got a PhD in mathematics in 2008 from Novosibirsk State University in Russia. And then he became a docent in engineering physics in 2019 at Uppsala University in Sweden. And she is presently working as a senior lecturer at Uppsala University, and as research within wave energy fields since 2012. She was involved in R&D at the Swedish wave energy company Sibased. Okay, she's group leader of the working group technology of wave energy converters and wave energy converters arrays, and a management committee member in WakeNet, Cost Action, a pan-European network for marine renewable energy. And her presentation today is going to be about grid integration of wave energy converters, research and experiments at Uppsala University. So, Irina, the screen is yours, but yes, you can go ahead.
Thank you very much for your presentation, and I'm very thankful also for inviting me to this webinar, and where I can talk about actually the work that has been done at Uppsala University. It's not only my research, but it will be, let me see, a research of the whole wave power group. It has been done during past almost 20 years. So I will start with a short presentation of wave energy conversion and the overall concept of that. Then I will speak about specifically Uppsala University wave energy converter, the project that was where we tested different wave energy converters, their connections, their power takeoff, and so on. And then I will talk a little bit more about the concept for electrical system, grid integration studies. And if I have enough time, I will talk a little bit more about why do we talk about wave power and why we don't like wave power. And also maybe some learnings and challenges from these studies. So, what are the wave energy converters? So basically what we would like to, is to convert the energy or the motion of waves into useful electricity. And to do that, we need several steps. So one needs to absorb the energy from waves, and in that case, we can talk about different primary absorbers. In that case, it's a buoy. Then we need a conversion, it's a generator, some transmission system, and then finally one needs a grid connection. And of course, one shouldn't forget about the impact on the environment and try to do the job so that it's economically feasible. Uppsala wave energy converter, it's so-called point absorber, meaning that we have a buoy which is placed on the water surface, and it's rather small compared to the wavelengths, and it's directly connected to a linear generator placed on the seabed, and it is moored by a concrete platform. It's not shown here, but it's just below this hull. So and the linear generator in that case will produce very bad quality electric power, because it will vary both in voltage, and the current will vary both in amplitude and frequency. Why it's been decided this way? It's simply because this type of wave energy converters has quite a little number of, very few number of moving parts, and that means it's more reliable. Most of the loads are related to electric loads rather than mechanical loads. All the expensive equipment is placed on the bottom, and this is protected from the waves, which are much stronger in the surface. And this is one of the WECs which has been longest operating actually so far in the at least among the wave energy converters that I know. This device is relatively small, so its installed capacity is about 100 kilowatt, not that much. So one needs to place many devices like this together and then interconnect them with underwater low voltage substation, and then interconnect those to medium voltage substation. And then we can transmit the power to the grid. So here one can see the first actually steps in the experiments. We have done some studies from the source perspective and seen how much energy is actually available in waves, and how the energy conversion will be happening inside the generator. We built our own test rigs at Uppsala University and tested. This is one of the first linear generator prototypes built there. And on this picture, I'm trying to find my pointer, here it is. So this is the first prototype which has been built, and it was deployed offshore. So that was in January 2007. Since then, quite many experiments offshore have been done. So where was it? It was nearby the town Lysekil, and that's why we call the Lysekil project. So I'm physically actually placed in Stockholm, but I work at Uppsala, and Lysekil is just on the west coast of Sweden. And this is how the wave power park looked like. So we have at the site some equipment installed. So this is a short overview. Maybe the most interesting part is about the wave energy converters. So this was the first prototype, and then 2 others were built with quite a lot of measurement equipment installed in them. Some others modifications on the electric circuit, on magnetic circuit of the generators, different sizing, and this is the latest version. And I think in total about 13 different wave energy converters were deployed at the site and tested there. The latest version, this L12, it's just the number of how many of them in designs were developed, is commercialized by a spin-off company, Sea-based. Uppsala University is actually one of the first universities, and that were the first wave energy converters which were tested in park configuration. And so one can see that in total 3 generators were connected. And in order to do that, one needs, as I showed, marine substations. So we designed first marine substation, which interconnected only, or which was built to interconnect only 3 wave energy converters, and it was deployed. Later, we built another one, which was capable to interconnect 7 of them. So we have constructed the connection point to the grid, and this is a so-called measurement cabin. So basically, this is where most of the control and other measurement equipment is installed. So here it's very short presentation and overview. Later, there will be a link to the website, or there will be URL. So if you are interested, you can always go to the website and read more, because there are many publications on that topic and one can read about that. Again, very quickly, I will just jump through. We, of course, monitor the sea states. We monitor the wave conditions at the place. We have also an observation tower which just looks into the sea, from which we can, for instance, see the buoys, or install cameras, etc. So we have also done some biological studies at the site. So the most interesting part, operation of the wave power parks. The overall concept was like this: since the electrical power from the wave energy converters is quite ugly, so it was transmitted. It literally looks like this. It was transmitted to the low voltage substation, and there it was converted to the 30 Hertz current and voltage, and then it was transmitted to be connected to the grid. So looking from this point of view, if we have several WECs, then we will see this type of voltage. This is 3-phase voltage recorded from experiments. Then it was rectified, connected to the common bus, and then we could invert it. Then we had also transformer placed at the same substation, and then it was transmitted to the grid. So what experiments have been done? A lot of work was made on connecting single wave energy converters and wave power parks to different loads. Like if we connect to this resistive load, another resistive load, and so on, how much control do we have over wave energy converter? So we had the dump loads on the seabed, we had dump loads next to the measurement cabin. We used also diode bridge rectifier to see to utilize for the wave power park studies. There was also so-called resonance circuit designed and tested. And the grid point that I showed earlier, it was built, and we have tested all the equipment in the lab, and different parts of the grid connection were also tested and validated. But unfortunately, it's never been operating with the grid, or we never had wave energy converters operated with the grid. And again, below here on the 2 plots, you can see results from experimental studies. So we had voltage, 1-phase voltage, I think it was red curve from one generator, blue one from another generator. Then we had a common DC voltage at the bus bar measured. And here one can see how improved performance of the whole power park looks like, again, from the experimental point of view. The red curve corresponds to the power output from one converter, blue one from another converter, and the green one is actually the power from the wave power park. It is a substantial improvement, but it is very much irregular. So how do we make sure that we can put this kind of input to the grid? So as I said, since we couldn't really run wave power park experiments with the grid connection at the Lysekil test site, so we applied to Marinette to have some tests with the power hardware in the loop, that installations that they had there. And this picture presents what they actually had. And what we used one installation where we had wave energy converter, a single wave energy converter integrated into this grid, but we also like disregarded this part and only considered injecting current as it would correspond to a wave power park at the DC bar in the back-to-back converter here. So what we have tested one wave energy converter, and that was with a WAMIT model. And then we used 3 and 10 WECs. So basically a very small park as it was tested offshore, and a little bit larger with 10 devices. We used for park configuration, we used the data from one of offshore experiments, and we just calculated what should be the power from the park at the DC link, and injected current according to that. And we considered different configurations. So in reality, it's quite hard to figure out, or the interaction between converters is substantial when they're placed in the sea. So, and to see this interaction is a complicated task. So we just considered the worst case when, say, the power flow from all devices comes at the same time simultaneously, and when it is shifted in time. And it could be shifted in time with some regular steps or some kind of randomized shift, which gives more or less reasonable representation of how the power flow would look like from the from each WEC when they are interconnected in a park. So from this point of view, we can see that the power from a park varies substantially, but the average lays quite low. And if we look into this average, we can utilize energy storage to obtain a reasonably good power output, and to control the current and voltage injected to the grid. Another is how do we deal with flickers and harmonics. And again, the solution here is using a reasonably large energy storage. Then from inertia emulation, again using wave power parks, and unfortunately, not like Bernardo was telling before, we don't have any rotational inertia in the system, so that we can take out more power than necessary. That utilization of an energy storage could help us to mitigate the disturbances in the frequency. So basically, we can see here that, yes, when there was a disturbance, I think, at this level, when the frequency dropped down, so more reactive power was injected, and in that case, the power from the energy storage, in that case, it's a battery, was used. I see I still have a couple of minutes to complete my presentation, so few words. Why do we talk about wave power? Obviously, it's environment. It's some reasoning based on physics and economy. It's a renewable energy source. It's proved to be a good artificial reefs offshore. Usually they are located quite far offshore and they don't have that high visual impact as, for instance, wind, offshore wind. And in most of the cases, no dangerous materials are used in that case. But of course, it has to be checked depending on technology. From the physics point of view, waves has the largest energy density per meter of the wavelength, again compared to the sun and wind, and that brings a slightly different utility factor on it. And the power available worldwide is quite high, and even if we look from the how much wave power is actually available next to the coastlines, then yes, between 50th and 70th latitude, we see that there is quite a lot energy available as potential. And even in Europe, this is a bit close up, we had quite low potential around Sweden, but we did test in Sweden as well, and it showed that we can extract a reasonably high amount of power if we build larger parks. So from the utility factor point of view, since waves has a much higher density, energy density, and the availability of waves is a bit different than for solar or wind. So we can achieve a higher utility factor, meaning that quite high time when the wave power park operates at its highest capacity compared to PVs and wind. However, it's still emerging area of technology, and there is no actual solution yet. It has been also noted that the availability of wave energy corresponds to the electrical demand on average annually over the years in at least in the northern hemisphere of the Earth. And then very quickly, why we do not like wave power, and this is due to a very large variability on the technologies. Unlike in wind, there is no clear trend on which technology will be winning. And I placed this picture just to illustrate some of the very few concepts. In reality, there exist around 150 or even more than 150 different technologies. And everyone is working on developing their own. Survivability is a very big issue. The machines had to be built to withstand very large waves, but they do not always operate at large waves. Get power, electrical power to grid or to the shore is another challenge if the machine is not always operating at this highest capacity. So that may lead to very large losses and very low efficiency of the electric system. Cost, everything which is done offshore costs quite a lot of money, and one of the challenge here is not that much actually can be done in the lab conditions due to the difference in physics. I know many technologies which were tested successfully in the labs in a smaller scale, but they never came out to offshore testing simply because it's difficult to upscale. And therefore, there is very little studies on what the electrical power could be available from wave energy converters. Some of learnings and challenges which I was a part of, as I mentioned, lab experiments, they're very much limited. Limited by the power capacity, limited by physics, especially when it comes to the testing in wave basins. Experiments, offshore experiments, they may fail due to different reasons. And for example, we had planned to test wave power parks once again, and that's why the grid connection point was built. However, we never came to this point simply because due to different reasons, the installations offshore failed. Sometimes it's something that you don't even expect. You transport your converter to the site, planning to deploy it, and during deployment process, something breaks and converter is not operational anymore. So, and everything delays with another half a year while things can be repaired. Overall efficiency is still a question, and that's linked to the utility factor. Among the wave energy converters which were tested so far, they were very large with very large install capacity, but unfortunately, this company is bankrupt. So now we have either things laying at the bottom of seas at different locations, or they are not operating anymore. Companies do not exist. And considering all the above, the questions related to grid integration are even more challenging. And for example, planning for a transmission system, it's supposed to be, there are many questions related to economics. For example, any conversion process is supposed to be done perhaps offshore. And should it be done at the underwater substation? Should it be done at a platform, or should we build something floating? In any case, the substations, no matter if they're placed on a platform, floating, or underneath water, they're very expensive. And unlike offshore wind, it might be too expensive for wave energy converters to have this kind of transmission systems. One can say, okay, we could optimize the power level on the whole power park and on the whole electrical equipment, etc. But this is also a very challenging process. I think perhaps it could be done on the company level, but from my perspective as a researcher, there is very limited information available on the equipment. The equipment is designed for offshore wind, which is basically at another power and voltage level than wave energy converters could operate. And the cost is also not always known. So availability of power equipment, yeah, we know that AC power equipment is available, and we can try to find more information about that. But for HVDC transmission, for example, or even medium voltage DC transmission, power equipment it's still a research area. So, and I'm sure there are much more points to mention here, but I would thank you. And in case you're interested to read more about research that we have done, there is a URL here. So thank you.
Thank you very much, Irina. Thank you for your very interesting presentation. I don't see any questions, but I have myself, I have some questions to make you. You talked about energy storage for power smoothing. Is this energy storage system of what type? Is it compressed air systems? Is batteries? Is what type of energy storage system you use?
We use the electric energy storage system. It's batteries and ultracapacitors.
Okay, and if we conceive the possibility of these energy converters, these wave energy converters participating in frequency control, as Bernardo has just discussed, you can kind of deload the converter in order to be capable to deliver this kind of service also from the side of the wave energy converter systems?
I believe it's very difficult because we don't have any rotating inertia as it's available with wind energy, and mainly different energy storages could be used for frequency regulations. I don't see the way that we can load more the generators in that sense.
Okay, I see. Okay, I also, well, now we can have a short time for some discussion, and I also would like to ask Bernardo see the developing hybrid solutions in terms of different technologies offshore, like devices together with wind power and wave energy. How do you see about the feasibility of this solution as a whole? How would you develop the solution in terms of so defining the substations, the layouts? What is your idea?
Okay, Professor, your connection failed 2 times, I believe.
Oh, sorry.
Yes, no problem, but let me check.
Have you understood my question?
Let me check. You asked about hybrids offshore farms.
Yes.
How do we manage to deal with them with different technologies? I mean, okay. Well, I believe that we could see from the presentation from today, from mine, from Irina's, that we have a complementarity here. One technology can do some kind of things, the other can't. At the end, both deliver electricity, but they can be complementary. So I believe that two control layers should exist. One is more a management layer to smooth the overall farm response in terms of power to the mainland grid. And then there is another layer for the provision of support, which we can tackle the support knowing the limits of each technology. For instance, if we are dealing with the primary frequency control, we've seen today that it's extremely difficult to do it with wave energy, but we have the offshore farms. Perhaps the wave energy can help offshore farms on mitigating wind variations by storing energy or whatever. So these topics are, in fact, will be studied in EU SCORES project, which was accepted. It's now a project in September, and me and Irina, INESC TEC, Uppsala University, are working there along with other partners, specifically to deal with these issues. Not only, but also to deal with these issues. I don't know if I answered your question, Professor.
Yes, you quite responded to the main issues I wanted to be tackled. But so what you mean is that for instance, the provision of frequency services in this case would be up to the offshore wind farms. So they would be the responsible for the provision of this type of services, of balancing services. What about solar PV? What about it is also possible?
That's what I was going to say.
Okay.
Yes, depends on what we have. In this project, we are going to study two combinations. Three can also be done, but the budget did not allow this. We are going to study wave plus wind, I mean, in Portugal. And in Belgium, we are going to study PV plus wind. So, of course, in this PV plus wind, both of the players can provide frequency support, but just one of them can generate during the night.
Right. Okay, I don't know, Irina, if you want to add something else more.
I mean, the challenge here is how do we maintain the power supply from renewable energies and at the same time staying economically viable. Of course, we can build a very large parks and we can say, okay, wind is free, solar irradiation, solar energy is free, waves are also free. But if we curtail some of them, will it be still feasible for the technology owner or to actually provide or build these power parks?
Okay, well, I think we can finish now. And before finishing, let me, on behalf of INESC TEC, thank you for your availability to be here with us and presenting the views you have about the possibilities of exploring renewable offshore energy. Thank you very much. And there's a question. I see there's a question. Yes. This is a question about bird problems that may be near turbines and may be heated by turbines. This is a non-technical problem. It's another type of impact problem. Do you? I mean, this is for both of you. Does any one of you wants to add something else?
I've never seen a bird attacked by a turbine. I've been close to several wind turbines and never seen a bird near dead in the floor, but I believe it happened. I also know that there is a lot of noise coming from wind turbines that could put birds away. I don't know if this exists, they could happen, but I'm not quite sure how we can deal with that. We know that we have problems related with the CO2 emissions and other greenhouse gases, and we have to choose. I'm not saying we need to kill birds, of course not. I even like them, but the issue is that we are working to get more renewables to the system to avoid climate change that we already see, and this also affects the birds migration and so on. And we are working on that. I cannot quantify how many birds have died because they were killed by a turbine.
Yeah, I think there's a solution for that. Is when building the offshore wind farm, be sure that the offshore wind farm is not on the route of the migration of those birds. This is a very wise approach to try to solve the problem. Exactly. Otherwise, I don't see any other way. Maybe Irina, you want to say something else?
I totally agree with you, João. It's first of all, one is to study where the birds are traveling, and second is if we are going quite far offshore, then birds will anyway travel much closer to shore than flying over deep seas.
Yeah. Okay, so I think we finished. Once more, let me thank you for your availability. It was a very good webinar, and we will keep in touch for the coming years for sure. Thank you.
Yes.
Thank you.
Bye,
Bye everybody.
Bye.
Thanks.